How does quantum measurement affect Bell states? Imagine holding two magic coins that are perfectly linked so that flipping one instantly reveals the result of the other, no matter how far apart they are. That's similar to what Bell states do in quantum physics. Bell states are special pairs of particles that are deeply connected through a property called entanglement. When you measure one of these particles, it's like opening a surprise box that instantly determines what the other contains. But what exactly happens when you perform a measurement on these states? That's what we're here to explore. Bell states are for types of maximally entangled two-qubit states. They are like the most tightly woven pair of gloves, where the state of one glove instantly tells you about the other. When you measure one of the particles in a Bell state, the superposition, or the blend of possibilities, collapses. This means the wave function, which describes all the potential outcomes, suddenly chooses a specific result. For example, if the Bell state is a superposition where both particles are either both 0 or both 1, measuring the first particle will randomly give you 0 or 1. But once you see that result, the second particle state is immediately known and fixed. This measurement process doesn't just reveal information, it also changes the state itself. Before measurement, the particles are entangled, meaning their states are linked in a way that can't be explained by classical physics. After you measure, the entanglement is broken. The particles are no longer in a superposition but are now in a definite, classical state based on what you observed. This is called the destruction of entanglement, and it's a key point in quantum mechanics. The act of measuring forces the system into one specific outcome, removing the quantum connection that once existed. Now, in some cases, scientists perform what's called a Bell state measurement. This is a special kind of joint measurement that determines which of the four Bell states the pair is in. It's a vital step in quantum protocols like quantum teleportation, where information about a quantum state is transferred from one place to another. When a Bell state measurement is made, it effectively converts quantum information into classical data, which can then be used to recreate the original state elsewhere. In practical terms, Bell state measurements are used in many quantum technologies. For example, in quantum teleportation, the measurement outcome helps reconstruct a quantum state at a distant location. In quantum key distribution, the correlations from Bell states help ensure secure communication by making eavesdropping detectable. And in quantum computing, Bell measurements are used to read out entangled qubits and correct errors. To sum it up, when you measure a Bell state, you collapse the entangled superposition into a definite outcome. This destroys the original entanglement but reveals the strong quantum correlations that make Bell states so useful. These effects are at the heart of many quantum information processes, making Bell state measurement a fundamental tool in the rapidly growing field of quantum technology.